And please ask him as many questions as you need.
Yeah, please feel free to ask questions and fate came back. Today I'm going to talk about, again, subgroup tests that I eventually didn't define last time. So I wanted to explain what are subgroup tests yesterday and I didn't have time. If you remember the table from yesterday, I discussed a lot about the Aldous Lyons conjecture, explained it in two different ways, both via invariant random subgroups and via graph limits. And I'll recall the invariant random subgroup definition in a moment, so I don't assume that you remember. But I also said that there is a problem about what's called characters of the free group, which is called Kahn's embedding problem. And I say that this problem, through a sequence of results, is related to a specific complexity class called MIP star, and that our main proof method is filling up this bracket such that the relation here will be mirrored here. Okay, so these are the subgroup tests. These are the analogs of non-local games, and I'll explain both what non-local games and what are subgroup tests, and tailored non-local games. So again, this is just some subclass of non-local games, and I'll explain what is the subclass and what are non-local games. Okay, so a quick recap on the important things that I need you to remember. So yesterday we had a finite set, which was our alphabet. Okay, it was the set S, and it's finite. And the algebraic object that I care about was the free group. So it's the set of all words on this alphabet and its formal inverses. And with this, as any group, it has its subgroups, and I denote it by sub, the free group of S, the collection of subgroups over this group. And then I discussed random subgroups, okay, some random variable that samples for you subgroups, right? So it was the Borel probability distributions over the space. And that was too big of an object for me. I wanted to focus, because of the relation to the Benjamin-Ishram convergence, I wanted to to focus on a specific subset, actually two subsets of the probability measures over subgroups. So we said that the free group acts on its subgroups just by conjugation. That's conjugation. And you can ask which probability distributions, pi, for any element in S that I choose, I can first sample an element from this probability distribution, get an H, and then conjugate, so act with S, and get SH S inverse. And the question, if I do that, I get a new probability distribution. I want this new black box to be the same as the old one. This is called an invariant random subgroup. Okay, for any S this is satisfied, it's called an invariant random subgroup. So, and we denote them by IRS of the free group. Now we saw that there is a special way of generating a collection of IRSs, which is, I call it finitely describable. Okay, so finitely describable.
You average over S over that.
Okay, so if you want the simple random walk, you need to average. But here the point is that in Schreier graphs, your neighbors are labeled. You know to which neighbor you can move, as opposed to like an unlabeled graph where you don't know. So here I generally want for each direction to be a conjugate invariant. Yeah, that's a small.
It's a bit stronger, or?
That's stronger because a labeled graph is stronger. So you see from your local view better in which direction. Like just you can define more walks on a labeled graph than on an unlabeled graph, right?
I just meant that the
Yeah, it is
condition is a stronger condition.
Yes, but I'm just claiming that it's okay. So there are ways to translate the labeled case to the unlabeled case using like some simple tricks. So somehow you can, in an unlabeled graph, do some bisectric subdivisions and add some loops and stuff like that, and like recover labels in some sense. And then you can also see like directions by like looking at the ball of radius, I don't know, some radius around the vertex, and still be able to do this specific conjugation invariance. But that's like the property that I want in this case of the edge labeled graphs.
So just to make sure.
Yeah, sure.
IRS of FS is a collection of probabilities.
And a specific IRS is a probability distribution with this property for any S in S. So for any generator, which means for any word in the generators, you have this property. And that's the same as in some graph, doing a single step in the graph with a specific direction along a specific like label, and then replacing your root of the graph along this label.
Yeah, so the distribution is really about subgroups and position your group element.
No. Like subgroups. Okay, so that was the, I wanted to recall that as well, so you're a bit going faster than what I want, but let me just recall, if you have a subgroup, let me just, an IRS is a distribution over subgroups, just a distribution, that satisfies the following property. If you sample according to distribution and you conjugate by a generator, you stay with the same distribution, and this is true for every generator.
People are confused about the connection with graphs, so.
Yeah, that's what I started now saying. Wait. That's what I started saying here. So you have the Schreier graph of the free group, the Cossack Schreier graph with the free group with respect to this subgroup with the generators S. This is a graph, and it's a rooted graph. That's already, I don't need to pick a root. The root is the identity quotient. Okay, so this is the translation. An IRS with no specific vertex, like with no specific element of the group, translated automatically to a rooted graph, not to any graph.
No, but Michael, in
That's true.
IRS, you sample an H, right?
Right? And I'm translating it to you. If you get an H, you can generate a rooted graph, not just a graph. This is a rooted graph, with the specific root being the identity. So you don't need to choose a specific element here. That's the point. Or a specific Cossack. You have a Cossack of the identity.
No, but the IRS, I mean, conjugation is going to another vertex of the graph, so if it's an IRS.
Wait, so you say, okay, what is the relation between conjugation of this subgroup and what happens to the Schreier graph? So you can check that this Schreier graph as a rooted graph, okay, Fs, Sh, S inverse, S, this is another Schreier graph. That's actually on the level of the graph, it's the same graph, but you change the coset of the identity. The coset of the identity here is what was the coset SH before or something. Maybe S inverse H, I'm not sure. Either SH or S inverse H. So it's this operation is exactly changing the root of the Schreier graph. Okay, so that's the relation to changing the root. Is this like the one what you meant, or?
And Michael, just but to be clear,
Yes.
like in the word above, you were defining IRSs.
Yeah, that was completely group theoretic, but that's a dictionary that moves you from subgroups to graphs.
And this is like the translation that we also talked about yesterday between
But I've
the.
done it very briefly, so I'm dedicating time to that now. Yes.
So, okay, I just wanted to understand that.
I actually wanted to do it in a moment because I'm going to describe another form of IRS, but you pushed me to recall that whenever you have a subgroup, you have a rooted graph. This is the dictionary that moves you from the space of subgroups to the space of rooted graphs. And if you have a random element here, you get a random element here. And we saw that the definitions of, okay, an IRS translates to a network, a unimodular network. And what I'm going to describe, a finitely describable one, are exactly the finite graphs. Okay, and their closure will be the sopic networks, according to the metric that I'm going to define. So I also didn't recall what is the approximation notion in this probability distributions, but I will recall it in a moment. Okay, so bear with me. Any other remarks or questions? Oh, okay, great. So what were the finitely describable things? So I said that you need an action of your group on some finite set. That's a finite set. But at least for the free group, it's very easy to generate such actions. It's just sending your generators to any permutation that you want. So such a thing is always encoded as a function from the elements of S, just from the finite alphabet, nothing is infinite here, that's important, to the permutations on the finite set. That's why we call it finitely describable. That's just a finite list of permutations, right? That's the important thing here. And how does it generate an IRS? I claim that there is like a way of choosing a random subgroup out of it. So you do the following thing, the sampling mechanism. Sampling mechanism is first sample a uniform, and here it's important, uniform V inside omega, okay? And then you need to choose a subgroup output the stabilizer of this vertex, which let's recall, it's all the words in the free group such that this word acts, and again, I said that any action can be encoded that way. You need to recall how do you encode it that way and how do you record the action back, but that's very easy. W.V is equal to V. Okay, so all the words that act trivially on this specific vertex. Now, like I had this discussion both with Avi and Irit yesterday, that there is a very nice Schreier way of looking at this object of stabilizers. So let's recall again, like what would be the Schreier graph in this case? Okay, and I claim that it's exactly the construction that I both described yesterday and also that was used in Ramon's talk to sample uniformly, not a uniformly, but a random 2D regular graphs. So what do? You just put the vertices. I'll give a specific example now. Say that S has only two elements, X and Y. Okay, and I'm acting on a group on a set of size 3. That's the smallest non-trivial example you will see. And now I need to tell you what are the permutations. So here is X. And here's Y. So you see these are two swaps. And I chose explicitly non-commutative two swaps. Okay, that's the simplest non-trivial example. And now you ask yourself, okay, what is the stabilizer of this vertex? So the answer is, if you do the translation that I described yesterday from like with the direction, I said that the direction I chose was important. It was important exactly because now when you want to read the stabilizer of this specific vertex, it's exactly all labeled paths that start and end in this vertex. Okay, so let's see that. For example, the path X is in the stabilizer here. But notice that the path X is not in the stabilizer here. Okay, because this is a closed path. It starts and ends at this vertex, but this is not a closed path. It ends somewhere else. And similarly, you can see that, okay, so X is in the stabilizer. Let's call this vertex V. So X is in the stabilizer of V.
White.
Hmm?
Maybe white.
The blue is not
More
so-
visible in the
White.
in the video.
Sure. Let me change that. So X is in the stabilizer of V. Y, X, X, Y, right? Y, X squared, Y is in the stabilizer, and Y squared is in the stabilizer, and so on. But you see here, Y squared is also in the stabilizer, and here Y squared is also in the stabilizer. So somehow this element is in all the stabilizers, but for example, X is in this stabilizer, but not in the others. So the stabilizers are genuinely not the same. And this is exactly because this graph is not transitive. There's no automorphism of this graph to translate one vertex to the other. So actually all the stabilizers are different. Okay, so this is the graph theoretic way of reading this specific subgroup. Okay. And for those of you who is easier for them to think about graphs, you can always draw the Schreier graph and think of all my like arguments as some paths, checking whether certain paths are closed or not.
And the IRSs are the same, not finitely describable, are the same when the graph is not finite. When the
Explain it.
set, sorry, the set graph comes.
Okay, so you can always think of the Schreier graph of the free group as permutations acting on some infinite cells. That's true. Yeah, that's true. Like you can view this viewpoint also in the infinite case. That's true.
And for anyone who doesn't like, algebra, they can think of this graph and works on this graph.
Yeah, that's a good point. Yeah, you can always just think about the graph as the object and not the subgroup. For me, as a group theorist,
You don't
that's
have a-
easier
yeah, you
to
don't
think of
have a
subgroups.
distribution.
Yeah, the problem is you don't have uniform distribution of the vertices in the infinite case.
That's true,
So
but
you
it
don't
doesn't mean
get
that there is
IRS.
no sum distribution, right? Like, so the IRS at least gives you some distribution over the vertices, right? And anyway, we said that everything is only interesting up to the automorphism group of the graph, right? Like everything is the isomorphism class. So yeah, like you just need to distinguish things up to isomorphism. So yeah.
So really the question is whether this finite set of graphs can approximate in a
Yeah.
to describe all of the.
Yeah, so as you just said, the Aldous Lyons conjecture was are the finitely describable IRSs of the free group dense or is, I don't know, it's a single set.
Yeah.
Is the set dense in the collection of all IRSs? And clearly, I need to recall at least what is the meaning of being dense in this set. Okay, what does it mean that a collection of IRSs approach another IRS? And I'll recall it now. Yes.
Can I ask a very naive question?
Yes.
So you gave here a particular construction, right? That you can send every generator to
For permutation? Yeah.
permutation of a finite set, then you define a measure exactly like this, right? It's a recipe. And I completely agree that this thing is finitely describable. You know it when you see it.
Right.
But is it clear that there's no other way to generate finitely describable IRSs not by this construction?
So usually people think of it as coming from the finite index subgroups. Then like for a fixed finite index subgroup, it has only one orbit.
Mhm.
And then it's the case where this is a transitive action. And the fact that I'm not introducing transitivity is because this already captures convex combinations. I don't need to now say convex combinations. This already includes all rational convex combinations. And that's good because now I don't need to say, first take the convex combination of these and only then take the closure. I can just ask, take the closure. So it just makes my life easier. I don't know if that's the right way.
Well, not transitive, you could just pass to a smaller subset of omega and you would have another IRS, right? So
Right, but the point is that you're doing the convex combination of these exactly by taking the uniform distribution here, but a rational one, exactly because like everything is finite, like counting. Other,
Can you spell out the answer? So the question was, is there another finitely describable IRS?
as I just
The
said
answer is
that,
no, that every finitely describable can be presented this way, but.
what do you mean by finitely describable? That's the question. So I claim that the natural object is finite graphs, but previously we had finite connected graphs. And here, this doesn't necessarily need to be connected. The reason I chose it that way is exactly because this encapsulates somehow rational convex combinations of connected graphs. And I don't need to say something of the form, that's just our choice. Like we could have described it in a different way, but this encapsulates all finite graphs, but not necessarily connected, which is somehow.
Think about, I know, infinite index subgroups with, which are of finite index in the normalizer, so.
Yeah, but then it's not related to Benjamin-Ishram convergence.
Yeah, yeah.
Like,
But it's
we
still-
chose this notion, not, we didn't want to call it that way for it to be confusing, but just, wanted to call it that way because it encapsulates Benjamin-Ishram convergence on already takes convex combinations and
Yeah, no,
I
I
don't
think
need to say
there are-
more, not-
you can describe finite, there are finite.
probably there are other ways,
Yeah,
clearly.
that's not the purpose. I mean, it's not.
Like,
No,
Doron
that's
has many
referring
words.
to.
No, like Doron and others have like you take, I don't, how is it called, the graph where you cut up the trees, the core graph of the subgroup? Every subgroup of the free group, which is finitely generated, has a finite description, right? But I'm not counting all of these because this is not related to finite graphs and I want to somehow keep the relation to finite graphs. This is a way of keeping the relation to finite graphs very clear, such that I just need to ask whether the closure of this is everything. It's
So
a
what I
compact
understand
way.
is that this is your definition of.
That's a yeah.
Yeah.
My question was.
Everything here everything was a definition.
No, it's not, but it's not relevant. This is the one that fits the Aldous Lyons.
No, that's true. Clearly, there are other definitions, and I think the idea of a core graph is the thing that actually distinguishes between those that are finitely describable in the free group and those that are not. But that's not the correct notion for the Aldous Lyons. That's the correct notion, and I want to focus on that. Great. So this is the question, and maybe I didn't even write it down yesterday. Louis Bowen, myself, Alex Lubotsky, and Vidik. No. And the goal today is to explain to you our theorem. But before that, let me again, let's devote some time to recalling. What does it mean that the sequence of IRSs, I prefer the notation pi for IRS, and you'll see, when you see pi, you should think of a proof. For those of you who are used to interactive proof systems, our IRSs will take the job of being the proof. So I call them pi's. So a sequence of IRSs converges to an IRS pi if for any finite set K, and we saw this notation. No, we didn't see that's notation, but it will be important in a moment. For any finite set K in the free group, you can always do the following. You can sample a subgroup. Again, so this is pi n. You sample a subgroup, H, and then you intersect with K. That's just a finite set of elements. So this process gives you a distribution over subsets of K, right? That's the push forward of this measure along taking intersection with K. So this gives you some distribution over subsets of K. So what the resulting distribution is just a vector in a finite vector space. And again, I can do the same thing as yesterday. This approaches this if, let me just denote it, pi n intersection K approaches pi intersection K for any finite set K in the free group. So that's the definition of approximation in our case. And yesterday I talked about balls, right? If you take these Ks to be the balls in the Cayley graph, you just get the definition of Benjamin-Ishram convergence from yesterday. Okay, so this slightly generalized the idea of a ball. Just choose any collection of points that are well defined before, and you get this number. Yes, Avi?
I just wonder if you have it for balls, you have it for everything.
Yes, of course, because any finite set is contained in a large enough ball. That's just an easier way than defining now a Cayley graph and the ball and balls. Like in a free group, every word is a word. It's just every vertex that has a label, I can just use the labels. That's somehow what's nice about the Schreier graphs as opposed to regular graphs. Every vertex has a name. In usual graphs, every vertex doesn't have a name, right? Like a canonical name in some sense, with respect to the identity. Okay, great. So we see the Aldous Lyons conjecture. We see that. Let me move to something that should be very clear to everybody here. But again, I presume people who are less coming from computer science and discrete math may hear this talk, so I'm going to define some basic objects. Yes.
Before you continue.
Yeah, great.
So it will be clear for me, like you have these distributions of subgroups and you're saying that they are converging if for every subset K I take.
Finite, that's important.
Finite, yes, but for every finite subset that I take and I ask and I look at these distributions over finite subsets of K, this converges in distribution, which just says the probability of outputting any given subset inside K by these pi and intersect K distributions will converge in the usual sense to.
Yeah, yes, that's exactly what I'm saying. I always think of these as finite vectors, just write like a distribution over a finite space is just a collection of numbers between 0 and 1. And then converging somewhere is just coordinate-wise, each number converges, right? And that's exactly what you just said.
Simplex, like, yeah, okay.
Great. So I have here the monoid generated by 0, 1, all finite bit streams, and a language. It's just a subset of this thing. Now, every language defines a decision problem. Decide whether a specific bit string, whether X and Y satisfies X in the language or not. Okay, that's your decision problem. And I don't know, like for computer scientists, it's so clear that this already encodes almost everything that they can care about, right? But let me just give you some examples for those who are less used to this thing. So the correct way of viewing that is not on bit strings, but on combinatorial objects. So those of you who were in Eagle's talk yesterday, he always thought like things should be parameterized by graphs, he said, or something like that. But clearly, everything that is parameterized by graph can also be parameterized by bit strings, just because finite graphs can be encoded as bit strings. So the kind of decision problems that we care about are on combinatorial objects. For example, is phi, which is a logic formula like a Boolean formula maybe. Formula satisfiable. So I can assume I'm using only AND, NOT, or gates, and then I can write formulas. Every such formula, I can just choose an encoding as bit strings, and then I can ask, okay, you gave me a bit string, it encodes some formula. Is this formula satisfiable or not? And then the language will encode all formulas that are satisfiable and will not include all the rest. Second example is graph G. Now finite graph, recolorable. Okay, so these are like well-known problems from NP, right? If you encode this appropriately, it can also be in next if you encode it succinctly and stuff like that. But the most naive way of encoding the graph is, for example, using adjacency matrix, and then this is known to be NP complete. Okay, third question. Are G1 and G2 pair of graphs, non-isomorphic? So this is well known to be in what's called co-NP, okay? But still, it's just a decision problem that you can ask yourself. And one last example, which is maybe the most famous one. Will M, which is a Turing machine, halt on the empty input? So I hope, like, again, everyone has questions, I really encourage you to ask, because that's an important notion, but that's quite standard probably for everyone here. So but please stop me if you need. Great. So let's think about it. To describe a language, what happens here? Usually I have a combinatorial object. So I have object, a property of it, and usually this thing I think of as a number. So in these cases, I kind of like distinguish between yes or no, but the property can be more complicated. For example, in 3 coloring, you don't have to ask whether the graph is 3 colorable or not. You can ask what is the maximum amount of edges that a coloring can satisfy. So it may not satisfy some of the edges, so there are maybe adjacent vertices that have the same color, but you can ask what is the maximal proportion of edges. When I say a property, I usually mean some proportion, which is not necessarily either yes or no. And you will see in our case, it will be a number between 0 and 1, similar to the proportion of edges that can be satisfied. And finally, you need to describe a parameter, C and S, two parameters, usually called soundness and completeness and soundness. And if this property, which I'll call value, so if the value is larger than C or larger or equal than C, I will include in the language, then the instance is in the language. The instance means this combinatorial object.
What is X and value of X? Okay.
Okay, the combinatorial object X, value of X. If value of X is greater or equal to C, then I will include X in the language. And when the value is smaller or equal to S, I actually need some generalization of a language, which is called the promised language. So here I need to put it in what's called the yes instances. And here I want to put it in the no instances. X is in L no. So maybe not all bit strings fall under this characterization, but those bit strings I want to put in a subset called L yes, here in L no, and the decision problem now will not be distinguished between in L and not in L, but just distinguish between in L yes or in L no. Okay. So this is a very general setup, and the reason I'm doing this is because my combinatorial object is very, I think it's beautiful, but you may see it, think of it as not that beautiful as I see it. And the kind of question that I ask about it is, I don't know, maybe will be not the simplest or the most natural to you, but this is a very general setup. So I'm preparing to you that that's the setup that I'm going to generate. I'll drink some water. Okay, time was. Do we take a break between the two?
As you wish. Speaker is the boss.
Okay. I think I will take 10 minutes. Okay, great. So, what is our setup? What is our combinatorial object? So, a challenge is a pair K, D, such that K is a finite subset of the free group with generators S. So actually part of my combinatorial object will also require you to encode me this alphabet, but that's not that important. That it's just something that's in the encoding, and we don't think really about the encoding at this point. And this function D is a function from subsets of K to 0, 1. Now, already we saw this kind of object, 0, 1 to the K, because the way we defined that some IRS approaches another IRS was exactly according to its intersection with finite sets. Right? So from a distribution over subsets of the group, actually subgroups of the group, but still these are subsets, we get some distribution over elements here, right? And IRS will give me already a distribution here, and I'm just saying this is a decision predicate, namely for any yes and no answers to whether something is in the subgroup or not, whether the elements of K, these are just words, maybe I write it that way, W1 up to WR words, here, this is K. So for any couple of words, I need to decide whether I accept, that's that thing I think about as an accept condition, and this will be a reject, the 0 will be a reject. So these are the rules of the challenge. I want certain elements to be in the subgroup and other elements to be outside of this subgroup, but maybe it's very intricately dependent. So if this element is in the subgroup, I want this other element to be out of the subgroup, but if this element is not in the subgroup, I want this element, yes, to be in the subgroup, and so on and so forth. Okay, so maybe this is any function, any impossible function from bit strings parameterized by K to accept or reject.
The Boolean function on the membership of K in the sub.
Right. Okay. a Boolean function on the membership. Now, again, I'm just defining a combinatorial object, and I want you to think of it as a decision problem, but you can already see some rules of interaction, okay? So you can think of it as if you have a verifier. This challenge defines to like some form of the following kind of interaction. You have a verifier, you have a single prover, but this prover doesn't do much. It's similar to PCPs where the prover generates an oracle proof and then you only interact with the oracle proof and not with the prover itself. This prover will generate a proof, but it won't be just an oracle that I interact with. It will be an IRS. So this prover generated an IRS pi. And now the verifier tries to understand whether this IRS should win or not. But it doesn't have the rule of whether an IRS wins. It has the rules of whether a specific subgroup wins. So what does the verifier do? The verifier pushes the button. It gets as output a subgroup H. And again, like you can think of this as the oracle that you're interacting with, right? This is an indicator function. It tells you for any element of the group, whether it's inside H or not inside H. And then the verifier will just evaluate. So it will take H intersection K and evaluate D on it. That's what the verifier will do. And this is now either accept or reject. So you can see that although I described it very combinatorially, this describes somehow this weird interaction where the prover gives you an IRS. The IRS, once you push it, gives you an oracle to a subgroup. And once the verifier has this oracle, it can just ask for any element of H of K, whether it's in the subgroup or not. It will recover H intersection K, and it can evaluate D on it.
And the prover acts first. The prover doesn't know what K is.
The prover knows everything beforehand. It knows what D is.
Okay.
It knows what K is. It knows what D is at this point. We will see in a moment that I will add like some distribution over challenges. Okay, but up until now, I described a single challenge, and that's what happens in the single challenge. Okay. Any questions about that?
The prover knows K and it wants to maximize the probability that.
We will see examples with a single. We will see examples with a single challenge, such that still the prover has no no way of winning. Okay.
Yeah, but even before that, the purpose of the prover knowing everything about K and D is to maximize the probability that the verifier accepts.
And that will be the property that I'm going to maximize, right? Like the property will be what is the maximal acceptance probability in this interaction. That's true, but I'm going to define it like formally using like just mathematical notations. But essentially that's what it is. That's a good remark.
And looking ahead, we'll have an infinite IRS that has high value, and finite IRSs will only be able to get low.
Yeah, that's the way we are actually refuting the theorem. But yeah, you're jumping ahead. But yeah, that will be the idea. Exactly.
But after
Yes.
what's going on here, like you could have defined this without this prover verifier thing. It's just
I define it without any prover verifier thing.
like the value of like the value of D on some distribution pi is this probability that like
Okay, so let me just write it. So given pi and the challenge KD, okay, the value
Pi is an IRS.
pi is an IRS. Actually, pi can be any distribution over subsets of the free group, but clearly I'm going to focus only on those that are IRSs, and later on only on those that are finitely describable IRSs. But now it's an IRS. The value of this challenge, when you run it against this pi, is just the expectation when you sample a subgroup according to pi of the value D of H intersection K. That's just a number, but if you think of it in the interaction setup, it's exactly the probability that if this proof was provided to the verifier, that the verifier will accept.
So what, I mean, if pi is chosen, what does the prover do?
Hey,
What is the gain here?
Any pi.
Okay, no, I didn't say any pi. For this specific pi against this specific thing, the verifier needs to push a button. The pushing a button is a distribution on its own, so this is the expectation here. So the verifier already needs to sample from the IRS, and for example, if you take a non-residually finite sopic group, you can see that there is no specific, like you can cook up a challenge that essentially just checks the relations of the group and checks that some elements are not in the subgroup. That's exactly like the kind of separation properties you want from residual finiteness. I'm talking to Doron for a moment, just because I'm trying to convince him that something will be interesting. I will come back to that in a moment. And if you look at it, you will see the finitely describable IRSs will never win with probability 1. That's because you don't have quotients of this group that separate these elements from the identities. But still, the sopic value is 1. Will be the optimum along all IRSs. Finite describable IRSs will be 1. So it is interesting on its own. No specific one will win, but somehow like they can win better and better. So like even for this setup with a single challenge, just the fact that I'm forcing the prover to use an IRS may hinder him. Okay.
Yeah, but I wanted to clarify, it is, the prover can choose any pi.
The prover at this point can choose any pi, but once it shows pi, the value just asks what is the acceptance probability given that it chose already this pi. Yeah, like that's just a number for now. Now, I defined
In some sense, the value of this game is.
Wait, we still don't have a game. We have a single kind of question in the game. I'm going to define a game by some distribution, but yes, keep on.
Yeah, the value of this game would be the maximum of all pies.
Yeah, and the question is what pies do I allow? That would be the question. But let me get there. You're right. You're going ahead. But let me just say that a subgroup test, so I defined a single challenge, subgroup test. Usually we denote it by curly T, like calligraphic T. It's just a distribution. Okay, let's say rational distribution, just because I want to encode everything as finite bit strings. So I want even the distribution to be something encoded as finite thing. So it's a rational distribution over finitely many challenges. So again, if you want to encode it, it's just the following kind of quadruple. You need to give me the alphabet. You need to give me a sequence of challenges, K-I-D-I. Let's say I goes from 1 to m, I don't know, some natural number, but finite natural number. And then you need to give me a probability distribution mu, a rational probability distribution on the set 1 up to n. So that's the way you should encode. It's a way to encode the information that I care of. But now it's not a single challenge like in this picture. The beginning is the same, but before I evaluate everything, I need to choose an I. So you sample I according to mu. And you don't evaluate D because I don't have a D. I have D1, D2, D3, D4. You evaluate DI, the one that you sampled, of the H intersection KI. Okay, so now the prover genuinely doesn't know beforehand which challenge it will be compared against. So that's a stronger setup for the verifier, right? It can have some probability underlying its actions.
The prover does know mu.
Yeah.
The prover knows
mu.
the prover knows the rules of the interaction, like in every interaction. So everything, all of this is known to the prover, but still maybe there is no IRS that maximizes its probability.
To stay close to, if you want to stay close to the language and description in proof system, this tuple is the input to the proof system, to both prover and verify.
Right, but it's a single instance of interaction. Usually when you talk about interactive proof systems, you try to prove something, right? The input would be a graph and you want to decide whether this graph is three-colorable using the interaction or something like that. Here I don't have it. This is a single game.
This is like the graph.
This is like a specific instance of a graph I wrote, a combinatorial object. That is still the combinatorial object. I'm not yet.
But that's how games are.
Right, that's the standard kind of game that we call it a test. I already heard that's a bad name. Maybe we should have called it a subgroup game.
It doesn't matter. The point is that this is analogous to a graph, and just like in a graph, your value can be how many edges can I color correctly, So here it's gonna be, what's the pi that will satisfy the most, get the highest value, satisfy the most
exactly.
challenges.
Exactly. So I didn't define it yet, but now we are going, now that I have this. So we have a combinatorial object, that's the subgroup test. Oops. And as both Thirit and Avi said, now I need to define the actual property that I'm trying to maximize. And I claim there are two properties, and that's exactly what Thirit hinted at. You can define the ergodic value of the test, which will be the supremum over all IRSs of the free group. Oops. Of the value of the test against the IRS pi. It's now you have double expectation here, right? Because you also have an expectation. If you replace this by a t, you have an expectation over I sampled according to mu. So this is the new definition when you of val t pi. You can take the supremum over all IRSs, and that's not the interesting object because these are proofs that are infinitely sized somehow. What we really care about is the sopic value of the test, which is the supremum only over the finitely describable IRS. And when you have that, you can think of this IRS as just some finite edge-labeled graph, and pushing the button is exactly falling on some uniformly random vertex in this graph, okay? And verifying this, asking what is the intersection, we saw that the stabilizer was exactly the paths that start and end at the same vertex. So the prover generated a graph. The verifier falls on a uniformly random vertex of this graph. It checks whether the words that it has are either open paths or closed paths when you start from this vertex. And only that's a 0, 1, that's a tuple of zeros and ones, yes and no's, no's and yes. And then it decides according to this bit string because it has a decision function. Okay. So that's a more operational way of viewing this, the sopic value. In the ergodic value, somehow it gives you an infinite graph and you fall on some vertex in an infinite graph, but you do the same. But I don't know, somehow for me it's easier to believe that you fall on some finite graph. I don't know, maybe it's not that better or worse, just the way I think about it. Great, so this is the analog of, the property will be the sopic value. And now the completeness and soundness parameters, so now I'm going to define to you a decision problem. Whoops, sorry.
The one Hebrew word I know.
It doesn't really.
It's a good
I
thing.
know, which I only learned a year after.
It's not used much.
We don't teach it fast
You should
enough.
have told me that before I came back.
Okay, so I'm going to define a language which we call soft val theta, and theta will be 1 minus the soundness parameter, which is just given a subgroup test T, decide whether the sopic value of T is 1 or the sopic value of T is bounded by 1 minus theta. So that will be our decision problem. And again, you can talk about interactive proof systems, but I don't think it's helpful for this context. That's my decision problem. In what complexity class is this decision problem? Or vice versa, if this is a complete problem for some complexity class, how large is this complexity? That's essentially the question. So we will see in a moment that it's not hard to show that this is in RE, and our main contribution is that this is RE. Okay, this is as hard as deciding the halting problem. Okay, so, and you should ask yourself, what makes the halting problem hard? What makes the halting problem hard is that you don't know how many steps you need to take, even if the algorithm is very small. Maybe you don't have any bound on the number of steps you need for it to halt. And here, the same thing happens you don't have any bound on the size of this graph. Even if it's a finite graph, you don't have any size on its size, bound on its size. And that's where the as hard as RE comes from. Okay, so the prover, to actually prove you the thing, maybe needs a huge, like even if your instance is small, maybe it needs something very, 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 very large compared to the instance to prove to you that actually this is an accepting condition.
Just to be clear, you're not, like, when you're saying this problem is equal to RE or anything.
There exists a theta such that.
Even though like in this problem description, you had like expectations and randomness and so on, this is not like a question that you want to answer probabilistically with an algorithm. You just want to say like you.
Why? No. I'm given a subgroup test and I'm questioning, this is a bit string. I'm asking you something specifically about this bit string.
Yeah.
Does it encode a test with value 1 or test with value 1 mistake?
Like your computational model here, I should think about like just Turing machines.
Yeah. Need to decide to distinguish between these two cases. A priori, it could have been in some complexity class that is much smaller than you could have decided it using a polynomial run, maybe an exponentially running time of some, but it turns out that no, it's as hard as the halting problem.
You're claiming that the value is continuous.
I'm not claiming anything. I'm just claiming that for this is parameterized by a
No,
theta.
but here, I mean, should relate to this problem of.
Oh, I didn't say it yet. How is it related to Aldous Lyons? That's a good remark. So Doron's remark is great. Let me write it here. But I want, before I'm getting into the relation to Aldous Lyons, I actually wanted to give you some examples of this problem and how it's related, for example, to NP, stuff like that.
And
But-
later you're going to show us that you can encode the halting problem into this language.
I'm not really going to show you, but I'm going to explain to you how we do it. Like actually showing all the details clearly is not enough. We don't have enough time, but I'll explain. Yeah, sure. Okay, so just Doron's remark is just that this function, fixing a t, if you just leave this bracket as an open input, it's a continuous function from the IRSs to numbers between 0 and 1.
Linear function.
Yeah, it's a linear functional, right? That depends on infinitely many things. So it's a continuous linear functional. Great. So that's the connection to Aldous Lyons. What do I mean by that? If the finally describable IRSs are dense and you have a linear continuous functional, then the supremum over the dense set and the supremum over the whole set should be the same. So at least Aldous Lyons, a corollary of that, this is continuous. And a corollary from that is that Aldous Lyons conjecture, maybe yes to Aldous Lyons conjecture, implies that the ergodic value of T is equal to the sopic value. And please remember that because I'm going to come back to it. To recall from yesterday's talk, to show the cons embedding problem is false, there were two theorems, one that related cons embedding to the decidability and one that showed that it's undecidable. So the first step will clearly use this idea. Yes.
So this answers my question that I didn't ask, which was why do you need a gap between 1 and 1 minus theta? Because if you just had a gap between 1 and less than 1, then you couldn't use that to prove your.
Right, exactly. It won't necessarily mean that.
You also have convergence.
Yeah, you can have convergence even though, yeah, they can approximate even if.
So then my question, follow-up is it much easier to prove this, that the halting problem is in this language without a gap?
Yes, it is, and it even actually nicely, Bowen knows how to show it using tilings. You can encode the undecidability of the tiling problem as an instance of a subgroup test with no gap. That's really nice. Like we had a complicated proof of even that, which uses compression. If you know, like the gapless compression is easier than non-gapless compression. Like just the steps of the proof are easier. And Thomas and I, like we were sure that we can do that before we understood that we can do the general thing, and we thought maybe we should write it, maybe not. And we discussed it with Louis, and Louis just said, wait, I think I can do it much easier through tilings. So it turns out that actually, like there are easy, quite like standard ways of deducing that the gapless case is RE. Yeah.
So I feel like I'm missing the punchline of the argument, right? So are you?
I don't have an argument by yet, but still.
Are you going to claim that the ergodic value is decidable? That you can prove that out?
Clearly not, but what we will see, and again, I'm like you're pushing me forward is that I have an algorithm that approximates this from above, and I clearly have an algorithm that approximates this from below. So if they are the same, I have an algorithm that calculates it up to any arbitrary error that you want. And that will be Aldous Lyons implies decidability of something value. But you're jumping ahead, I'll get there. But maybe let's stop the questions for a moment and let me just give you examples, because that is the new decision problem. Let's see how it's related to like more standard decision problems. Okay, maybe I'll do these examples and let's take a break, a short break, okay? Because I need a short break. So examples. So if you have a formula, phi formula, you can describe a subgroup test from this formula. And I'm describing only a combinatorial map. It's not on the level on encodings, so it doesn't really tell you which decision problem lives in which complexity class, yeah? But still, like this, even on the combinatorial level, it's good to see that this transformation. So given a formula, you can define the subgroup test. So this formula is on some collection of variables. So my set S will just be the same collection of variables. And my set K would just be read the value of these variables. So these are not words in the variables. These are just the variables themselves. This will be my finite set K. And my decision predicate will accept alpha if and only if the assignment xi maps to alpha I when I interpret 0 as false and 1 as true. Okay, so this describes some assignment to the formula, and this will be 1 exactly when this assignment satisfies phi. Okay, so for example, if phi is unsatisfiable, D is just the 0 function, right? So already we see that this is perfectly sound, right? If you take an undecidable formula, this test will never accept anything. Doesn't matter what the subgroup is, doesn't matter what the IRS is. So this translates P non-satisfiable implies that the sopic value of T phi is 0. Now, maybe it's not that clear, but I claim that when phi is satisfiable, you can find an IRS that wins with perfect probability. So I claim that phi is satisfiable. Then the sopic value is 1. So you just need to show me that there is an IRS that will always give me the same bit string. And I claim that there is a 2 vertex, like just use permutations on 2 vertices and you can find an example. Okay, so I'm not even giving you the construction, but I'm giving you the hint that enables you to show the construction. So again, under some appropriate encoding of the problems, you can see that NP is there. But you can define a maybe more interesting T phi instead of just checking the whole formula. If it's a formula that is built out of clauses, like a 3CNF instance, you can maybe just choose a random clause and only check whether the assignment satisfies this specific clause, right? And if you pre-compose with PCPs, you can see that even this can have a gap, right? Like the PCP theorem tells you that even this kind of problem, you can change your instances using the PCP theorem, and then you'll get, and I'm not assuming everybody knows what it is, it's just a gap generating thing for us at this point. Then it is in sopic value theta. Again, according to appropriate encodings of the problem. So maybe let's take a break. 10 minutes?
Right?
Yeah, and then I'll explain the Aldous Lyons conjecture relation.
Let's get back at 11:20.
So here, that's part of our first paper. There are 2 algorithms, so 2 Turing machines that given a subgroup test produce two sequences says, so one of the algorithms produce a sequence of alphas that can only increase if you run it enough time, it will produce the ith element of the sequence. And alpha I tends to the sopic value of this specific input. Okay, so I got the test as an input. Okay, and the other algorithm produces a sequence of betas, and these betas can only decrease and the beta i's approximate the ergodic value. So usually when people talk about these kinds of results, they draw this picture. This is a continuous picture, but again, like you can think of just like connected the dots of these things. So you have the number 0, you have the number 1. The a priori, the ergodic value is some number in between, and the sopic value potentially can be smaller, right? And our alpha algorithm is some function that has an asymptote here. You said that the blue is bad, right? So maybe let me.
For a picture, it's fine.
Okay. And let me do a green. And our beta algorithm approximates from above. Now, let me say something about these algorithms. This one is naive. The finitely describable IRSs are a countable set. Just order them, check the value one by one. You will get better and better alphas if you take just the best one you found up until now. Okay, so the alpha algorithm is, trivial. I don't know. You need this observation of countability. The beta algorithm is slightly more complicated. It turns out that although the IRSs are a very complicated set, they have outer approximations which are convex hulls, like that you can approximate using linear programs. So we can generate a sequence of linear programs that gives you the beta. So the first linear program gives you a number. The second linear program can only give you a worse number because it is more restricted, smaller. Okay. A smaller number because we have more restrictions. So the optimum is smaller than the previous one, and we add more and more restrictions. We get a sequence of linear programs that essentially approximate this very complicated convex set. That's the way you should think of it. So it's outer approximations of this convex set, and this gives you an algorithm just by linear programming.
So it is to say that like with outer approximation, you can describe IRSFS as like
an intersection of sets.
As like an infinite intersection of like hyperplanes or what?
Okay, so you define sets, convex sets that are much simpler.
Yeah.
That are defined by just a finite amount of constraints.
Yeah.
Okay, and the more constraints you add, the smaller set you get. Like you essentially intersect with more hyperplanes. But the optimum, the value is just a continuous linear thing. So the optimum can be still just calculated using a linear program for each one of these.
Sure.
And if you do it more and more, you will get more constraints. You will get a smaller value, which approximates better like this very complicated convex set. Okay.
Can you give an example of like the first linear program? What does it look like?
Yeah, so you just, you have the union of all the Ks, Ki's, just call it K. So everything depends just on the values that you get on K. But now, what is an IRS? It's a probability measure which is invariant under conjugations. So you can just take balls that contain K, larger and larger balls that contain K, and you just look which distributions are invariant under the generators, but only for the set. So this is a large ball. You have a small enough set such that its whole conjugation still lives inside the same ball. That's important. Okay, so there are only finitely many conditions of this form, like the expectation of being here should be the same as the expectation of being here because you're conjugate invariant. And since the balls are finite, you get only finitely many, and these are linear conditions. You have only finitely many linear conditions. You get the larger the ball, the more linear conditions you have. So I actually explained you the whole linear program. Yeah, you need just to force it to be a probability distribution, adds up to 1 and non-negative, right? These are like the basic conditions, and this invariance condition for bigger ball. Like the larger the ball, the more invariance conditions you check. Yeah.
You repeat it again?
Yes, like, what, okay, so every IRS I can restrict to a ball. Then I just get a distribution over like subsets of the ball, right? This is a set B. Like in IRS, you can push forward, like what I denoted by pi intersection B. You get some distribution over 0, 1 to the B, over subsets of B. My claim is now, what does it mean in conjugation invariant? The probability that you get a specific subset is the same as conjugating this subset, right? But maybe if you take this subset, maybe if you take very big subset and you conjugate it, you get outside this ball. I don't add this condition to the set of conditions that I want because I cannot implement it in my local view of the ball. When do I add an invariant condition? If this is a, okay, this is not the ball, this is our subsets of the ball, right? Like I need to explain like a probability distribution. Like a specific subset, if it's sent by conjugation to another subset, okay? I want its probability to be the same because I want to be conjugation invariant by definition. Like that's conjugation invariant, right? The distribution doesn't change under conjugation. So I can, like the ball tells me which conjugations I actually check because the larger the ball, I have more and more conjugation constraints.
And why does it converge from above to the ergodic bottom?
So clearly every IRS satisfies all the conjugation conditions automatically. So if you maximize over the IRSs, you cannot get something larger. It lives in the olives. And you can show that at some point you will get like this is some topological argument that the intersection of all these conditions is an IRS. Like it's just a claim about sets. Like if you take like the set that is defined just by these local conditions with intersections on local finite sets, if you take the walls larger and larger, it sounds like
So you know that
if
this
you contain everything, you will get the IRSs. That's a topological argument.
You won't get anything else.
You won't get something larger, yeah. Like it genuinely gives you back the IRSs, yeah.
you can compute the distance in the set of in the subspace of subgroups.
So
Given-
this is the distance.
This
This is finite, and the way I define convergence is exactly using these finite objects. So it plays well with the idea of convergence, yeah. That's the way you should think, right? Because my convergence was this kind of convergence.
But so in a sense, this doesn't actually give you any new information about what IRSs look like.
No.
You start with the IRS, you basically just discretize it in a sense.
I cut up,
Exactly.
like, what can I say about an IRS in the finite volume of the group? That's all I can say, right?
Because the natural question here, now that you know the answer is no, is what does an IRS look like that is not approximated by finite?
Right, and the
This
claim
doesn't
is,
tell you anything about.
it tells you something, it tells you that this approximates it from above, but it doesn't give you, you will never probably, like, as we discussed in the break, like, we don't know how hard it is to evaluate it, like, this is as hard as the halting problem, evaluating this, we don't know how hard is this, it's conjecture to be co-RE, and I think there are students, at least in the MIP star world, that try to show like that the analogous problem in MIP star is co-RE, but it's not yet written, so we don't know, but I presume that choosing an element in the IRSs is very hard, like your question is, understanding this set, both the upper set, closure of the upper set and the lower set, both are very complicated as convex sets.
It could have been that the ergodic value is decided.
Yeah, it could have been.
It wouldn't consider-
The IRSs are nicer than the closure of the IRSs in many other ways, but still, it's not known, and I think they conjecture that it's co-RE. And they have some reasons, like that many of the machinery of MIP star is equal to RE already transfers to like the completion version.
So call it because you can approach from above.
Yeah, exactly. It's
Well, we
in,
know it's RE.
it's RE because you can approximate this for below, and it's for sure in co-RE because you can approximate for above. That's a good remark. So the reason this is at least contained in RE is because of this approximation, and the reason deciding the upper one is contained in co-RE is because of the upper approximation, but we don't know that it's complete for this computational class. For the lower one, we know, for the upper one, it's open. Okay, let's move onwards. So we have this, let's just write the corollary. So combining this fact. Okay, so maybe let me give you the picture. Say that the Aldous Lyons conjecture is true. Then these are the same line So this is not the picture. The picture is that you have a single line, and the upper algorithm genuinely gets to the sopic value as well. So for any error term, and that's where the gap gets into, for any predetermined theta, once the distance between the alpha i's and beta i's is smaller than theta, for sure, either I went below 1 or I went above 1 minus theta. So I will be able to decide this problem. And actually, it's important for us, and I'll tell you why, that we don't restrict the theta beforehand. Usually you define it for a specific soundness value, like 1/2 or 1/3 or whatever. Here we don't have the parallel repetition theorem. And it's actually interesting. We don't know parallel repetition for subgroup tests yet. It's still like, if someone wants to prove it, I think it would be very interesting. And this means that the kind of result that we have is just that there exists a theta and a non-halting algorithm that we don't know to decide for it that is non-halting, that can be translated to soft value theta for this specific theta. So we'll see how reduction is not as good as in the MIP star case, where you can actually reduce to 1/2 because we don't have parallel repetition. That wasn't like a remark for the experts, but you will see later that this
But
will play a role.
you don't need necessarily parallel repetition, you just can't you like change the
You can change the model such that you have
Here's the
sequential.
challenges.
The question is like, you hate the picture, but whether I allow you to sample a single subgroup from the IRS, or I allow you to sequentially sample subgroups from the IRS. If I allow you to sequentially sample subgroups, I have a sequential parallel repetition that reduces the value exponentially however I want. What?
Sequential parallel
Sorry. Sequential repetition that reduces exponentially, and that's okay. But that's changing the model. My question, you just sample a single subgroup, but you check more and more about it. Does it still, does it reduce the value?
For those non-experts, just this parallel repetition, sequential repetition, just a way to reduce or to increase the gap between.
Yeah, okay, yeah, it's a mechanism of given one gap moving to a question where you have a bigger gap. Okay, so we just don't have any decreasing result. Like even polynomial decreasing result will give us enough to move to 1/2. Somehow it will be like exponential reduction or something, but still like.
But you don't really care about this, or?
We don't care because this already resolves the Aldous Lyons conjecture. I think computationally it is an interesting question. Like I do think this is modeled. There are nice questions about it. For example, does it have any parallel repetition? Does it have an exponential parallel repetition kind of result? I think these are interesting questions. Yeah.
Like, okay, one thing that I would maybe think about, like, does somebody suspect that theta equals a third should make this decidable? Like,
No, just my claim is that I'm not reducing the halting problem to a specific theta value.
right. But when you say that, does it mean that like for theta equals a third, this might be decidable?
I presume not.
Like,
But I don't know how to prove it exactly because I don't have parallel repetition. Your remark is exactly asking, do I presume that for some theta it's decidable? The answer is out of 1, like maybe for 1 it's decidable, but for any like number smaller than 1, I think it's undecidable because I think there should be some form of parallel repetition to this object. I didn't prove it, so I cannot claim that. Okay, but maybe it's even clear. I don't know. Like maybe someone needs to think about it. I don't know. Or maybe it's wrong. Like I don't know. Like someone should think about it. That's my claim actually. And I'll tell you that originally, you will see our proof method. Originally, we thought that we will need to translate all the, 15 years of developments in MIP star theory. And it took us like 3 years up until we got to this proof. And that was the problem, like all the deep quantum soundness proofs and the parallel repetition, we worked on it and we weren't able to show it. And you will see that we overcame it in a particular manner that was like that brought us back to the MIP star realm. And you will see the headline is Subgroup Test and a specific subclass of non-local games. And that was the epiphany, that we can somehow translate this model to a specific subclass of the MIP star model. Great, so let me just write the corollary. Aldous Lyons conjecture, yes, implies a sopic value theta is decidable for every theta. Okay.
Decidable.
is decidable. Decidable. Thank you. I'm not writing the important stuff. Sopic value theta is decidable for every theta larger than 0. Great. So I just said out loud what we tried to do. Like we now said, okay, like there is all these mechanisms of non-local games. We tried one by one to translate them to this, but it's really like so many like very smart people worked on this and were able to do the quantum versions, and somehow like just trying to do 15 years in 2 or 3 years, we weren't able to do it.
Yeah,
Like, even if we knew like what the ingredients are that we need.
clarifying what you're trying to do and they tried and succeeded is reducing the halting problem to sum.
Yeah, okay, so theorem. There exists a theta larger than 0. That's again us. There exists a theta such that sopic value theta is undecidable. And the way we do it is that we show that for any input Turing machine, there is an instance of soft value theta where the theta depends on the input, okay? But just in a polynomial manner, like the size of the Turing machine is n, then the theta is something like, I don't know, 2 to the minus m or something, okay? Like it's a bad constant, but it's still some constant that only depends on the size of the Turing machine. And then you can, if this was decidable, the Aldous Lyons conjecture, this is decidable for every theta, so you can decide for any Turing machine whether it halts or not. That's the kind of result that we have. Okay, so, and specifically there exists a theta that's so already for it, it's undecidable. Not claiming that it contains RE, but already for it, it's undecidable. Okay, so that's our result. And I said to move to a specific theta, for every theta requires some parallel repetition, like that's what it is needed. So that's it. Like but I want to explain this clearly. Like that finishes the argument, but let's describe this because that's actually 2 theorems. One is a translation theorem, and one is reproving MIP star is equal to RE to the subclass of instances. So let's talk about non-local games. Now, exactly as before, I don't want to talk about it only as an interactive proof system. I want to describe you a combinatorial object, a value for this combinatorial object, and some decision problem deciding something about this value. Okay? So what do you need for a non-local game? You need a graph, finite graph. The edges are allowed to be oriented. Okay? You need a distribution mu over the edges. So usually the vertices are called questions, and then edges are pairs of vertices. So these are pairs of questions, okay? In the usual formulation, I'm like intentionally defining it in this weird way. You will see why. Then for any vertex, you have a function which is called the length function. Oh. Length function that takes a vertex and outputs a natural number. Okay, so it tells you, that's essentially tells you, if I ask you this vertex, what is the length of the answer that I expect? Okay, you will see that that's what this encodes, but it's just a function from the vertices to natural numbers. And you need a decision predicate. So it's not a single decision predicate, it's a decision predicate for any edge in the graph. So if xy is an oriented edge in the graph, I have a decision predicate that takes bit strings. So F2 is the field with 2 elements for me. Okay? So it takes bit strings of length L of x times, so pairs of a bit string of length Lx and a bit string of length Ly, and it outputs either a 0 or a 1, so F2, back to F2. So I claim this is a non-local game. Now you should, those of you who don't know what a non-local game, okay, that's a bunch of data. Again, if the distribution is rational, this can be described as a bit string, that's important for us. But why is it a non-local game in the regular sense? Let me show you. So again, Irit, I'm sorry, but like this is the standard dramatization. I have a verifier here. And I have two provers. The verifier samples according to mu and edge.
So
and
non-local
says-
is multiple prover, that's the same thing.
The word non-local comes from quantum mechanics. This model models experiments that you can do in labs that actually shows that our world is governed by quantum mechanics and not classical mechanics. So the word non-local means that there are entangled particles that can like show you that you can win this game with higher probability than if the world was governed by classical mechanics. That's the reason for the name non-local, but
Meaning
for
that
us,
the provers are in very far away locations, but they have entangled stuff.
yeah, exactly. They are spatially they're further away than be able to be in communicating using light. So faster than light communication is not possible. And then you ask the questions, expect answers such that they couldn't communicate. The only way they can correlate with each other is using measurements of quantum stuff like qubits, essentially. But again, I don't need all this formulation. I will give you like some other mathematical way of doing it, but that's like why it's called non-local. Yes, sir?
No.
Great. But still, I didn't even explain how this encodes some interaction. So let's see that. The verifier samples xy according to mu. It sends, okay, so that's prover A and that's prover B. It sends the one endpoint to prover A and one endpoint prover B. Now the provers know the length function, so they need to answer a bit string of the appropriate length. So that will be some alpha in F2, the length of X, and that would be some beta in F2 to the L of Y.
Is this necessary? Why don't you give an upper bound on the maximum?
That's a good question. The reason is that in our tailored non-local games, the bit strings, like the quantum strategies, will be restricted on the way they measure each bit, and then I want a very strict requirements on length.
On different ones.
On different ones, and for each one will have a specific like restriction. You'll see that like in tailored games it will be important. Clearly, for the standard way of defining non-local games, I only need to just say, okay, what is the maximum of L's, and let's embed everything in the maximum, right? Like you don't need a length for each vertex. But still, you can like just ask the provers to give you a specific length of answer given you asked a specific question. That's okay, right? That can be part of the rules of the game.
Well, or another way is to define the decision procedure of the verifier, which you anyway don't specify. To look only at the first L of X bits of the.
Right, and I don't want to do it that way. Like you will see why.
Okay.
We need a good control on the lengths. Okay, so dx y alpha beta, that's something in this set, right? Alpha comma beta is in F2 to the L, X times F2 to the Ly, and it gives you either 0 or 1. 0 is reject, and 1 is accept. So indeed, like you can interpret all of this information as some interaction between a verifier and two provers, but still, I didn't tell you what are the allowed strategies for these provers. So let me tell you that. And that's, again, not the standard way of describing quantum strategies, but I will describe it like, just believe me, it's equivalent to a specific collection of quantum strategies. So a strategy, and I will say, for those who know what a strategy is usually, these are called synchronous. So it's an n-dimensional strategy. This will be a synchronous projective quantum strategy. So again, if you don't know what these words mean, great. If you do know what these words mean, so you know what to compare my model to, okay? But for us, it just will be an n-dimensional strategy. Will be a map, okay? S, that for any vertex, so for any x in V, Sx will be a unitary representation of dimension n of F2 to the Lx. So for any vertex, I want a unitary representation of F2 to the Lx. This is a commutative group, like it's a finite commutative group. It's not very nice, right? It's just a cube. Clearly, you can find Lx many unitaries that commute and that are of order 2. That's all it is. So you need to choose. This is usually called the observable form of a quantum strategy.
Okay, but Sx and Sy don't connect each other, right?
I'm not forcing commutation between Sx and Sy, that the images of Sx and the images of Sy don't need to commute. We will see later that it's helpful whenever there is an edge between Sx and Sy in the complete case to force that condition. But that's a very quirk of the way PCPs work. Okay, like it will be a quirk, not like something that I really want to be part of the definition. Great, but this is just a strategy. Now you should ask yourself, how is this a strategy? I'm going to define a value given a non-local game and this weird object, I'm going to define a value. That's why I'm calling it a strategy. And then I'm going to optimize all of these. Let's keep that.
Also, use vertex as its own length, but you always send it in the same UN. So
Yes, that's important. That's why I said it's an n-dimensional strategy. This n is fixed for all vertices. That's very important. You will see that otherwise we cannot get a value. We will see that. Okay.
Strategy is the same for both provers.
That's the word synchronous here. Yeah, exactly. That's a good remark. I force the two provers to use the same strategy, essentially. The same measurements on the same vertex.
You're going too fast.
And
Strategy,
wait.
strategy is a bunch of things. You didn't say anything about.
I didn't say anything about it. This is the object. Is this object clear? Yeah, it's just a collection of representations, right?
Right.
But Avi already sees that I defined only one collection of observables. And he knows that usually what you do is you define two things. Wait, let me just
Say
finish.
what the word observable.
Yeah, observables are the images of these functions. That I said just by that usually these are called observables. Okay, just the images of these functions are called observables.
Okay.
I will say that usually it's not defined that way. And usually you have different strategies for the A player and for the B player. And then you will have like SXA and SXB. And you have two kinds of representation. What I'm telling them didn't parameterize according to players, which means they have the same collection of matrices. Like they only have access to these functions, and they will be forced to use the same matrices.
And why is different?
That's true.
Ah.
But if I ask them, first of all, you can have loops, and that's an important thing. Whenever I ask for a loop, they will use the same matrices. That's important. Okay, I'm forcing them to use the same. And also, whenever I ask this one Y or this one Y, they will use the same matrices. That's the word synchronous here. And again, it's not a natural restriction. It's a restriction that is induced by the algebra. So somehow the synchronous strategies behave well algebraically, while the non-synchronous strategies sometimes are bad algebraically. And if you want to make just the algebra of your arguments easier, it's easier to work with these kinds of strategies. Actually, parallel repetition is harder with synchronous strategies. The way to prove parallel repetition for synchronous strategies is going through the regular proof with non-synchronicity and then to show some stability result about synchronous strategies. So it's not always helpful. For example, in the parallel repetition theorem, it's actually harder. But in general, most of the algebra is much easier when you don't let the two provers use different representations. They must use the same representation. And we don't know yet what does it mean to use the same representation. That's okay. I'm just remarking because Avi asked. Yes, let's see how is this defining some value, some probability of winning this interaction. Okay, so the way I'm doing it is the following. So tau is the normalized So it's 1 over n trace. It's the normalized trace on n by n matrices. It's average of the diagonal instead of sum of the diagonal. And I need another notation. Sx hat is the Fourier transform of Sx. And what is the Fourier transform? It's again a function from the same set, F2 to the Lx, but now to n by n matrices and not to necessarily unitaries, which just does the usual thing the Fourier transform does. So Sx of some A is the expectation over all B's in F2 to the X
Yeah,
minus 1 to the like dot product of A and B.
it's not effect. The
L of X, thank you. Thank you very much. Minus 1 to the A times B times the unitaries that you actually get from the B's. So Sx of B. That's a standard thing to do when you have a representation. That's just the projection on the common eigenspaces of all these matrices. Because they commute, they are mutually diagonalizable. And these are just the projections on the eigenspaces that are parameterized by these bit strings. Some of them have a +1 or a -1 that will just be translated to a 0 and a 1. Okay, so think about it. That's just, these are just projections.
Can you say again who commutes with who?
So this is a representation of this group. So all the images commute of the 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0.
Every X, all the SXs commute.
The images of all the SX of the
For
specific.
different X, they don't necessarily.
Yeah, right, yeah. But this transformation was for a specific X, right?
I don't understand what you just said. Projection on what?
This is a projection. This is a matrix. It's a projection matrix. Like it's
That's
squares.
a projection
It's a orthogonal projection. Yeah.
How do you see that?
All right, that's I can show you the algebra later, but that's an orthogonal projection on the space, the eigenspace, the common eigenspace of all the images of the standard basis here. I can show you later how to see that. And exactly the like this A times B will tell you whether it's in the -1 eigenspace or in the +1 eigenspace of each one of the matrices.
What?
Of these matrices all commute. They have a common diagonalization. What?
They have complex eigenvalues.
No, but,
+1,
but they're all.
They are order 2. They are order 2. They have +1, -1 eigenvalues.
No,
Oh, because
It's
it's-
a representation of F2.
I see.
Okay. That was confusing. So yeah. It's a representation of F2. Everything is of order 2, +1 and -1 eigenvalues. Yeah, that makes it much easier, right?
Yes. Okay.
Otherwise, it can have a more complicated structure. Yeah, thank you. Okay, great. But still, what is the value? So the value against. So let's give just this collection of information curly G. So this is a game for us. The value of this game against this strategy S is just the expectation of sampling X, Y, and edge according to mu times the sum over all AB. So A in F2 LX, B in F2 Ly, of what? Tau of S hat X A S hat Y B times the decision predicate dxy A B. Let's unpack this formula, okay? If you use like the standard formulation of quantum mechanics and the two provers hold a maximally entangled state, and they actually measure their maximally entangled state according to what these things tell them to, this somehow tells them how to orient their labs. Okay, they have like particles, they have like qubits, and this tells them how to orient their labs. They measure something about their qubits. The other prover measures something about their qubits. That's the probability that in their lab space, the result of the experiment is A and B. That's just a way of formulating the probability that in their labs, they will have an output of their experiment, output A, output B.
Why should it be?
That's by definition, yeah?
Why should it be non-negative?
Oh, that's a great question. This is a projection. It's equal to its square. You move it to the other side. Yeah, algebra. As I said, the algebraic arguments are very easy here. Usually you need to take anyway, let's not get to it, but in this format, everything becomes nicer. It's a positive, it's between 0 to 1, it adds up to 1. Yeah. Okay, so this is some probability. So we actually could have, the way to write all of these things is just the expectation that the measurements according to S produce exactly A and B. So that's a complicated way of writing it, but
No.
I just didn't define you how to measure stuff. So that's the
Yeah, no,
definition.
This is not,
That's a mathematical formula. I'm claiming that if you define what a maximally entangled state is, blah, 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 you will see that this whole expression, which is algebraic, and you agree that this is just a matrix, the trace of the matrices, some sum, and some products with 0 or 1.
I follow the expression inside the expectation.
Yeah.
I do not follow any of the intuition.
Yeah, it shouldn't be followed by someone that had never heard of a maximally entangled state or what is a measurement or whatever. I'm just saying something that this is very standard. Like for those who know what a quantum measurement is, the strategy essentially tells how to measure qubits that are in a specific kind of state, which is called the maximally entangled state. And this is just the probability that when they measure their qubits, they will get A and B.
So I mean, as a very, very special case, you can encode a classical strategy this way. And then SX will not be this whole thing. It will just be one a distribution over values, or even one A, like a specific choice of an answer A. For Y, there will be some specific choice of an answer B. And then this whole thing will evaluate to yes if it was A and B, and no otherwise. Or something.
Presumably that would just be the case for all the S-axis commute with each other.
Yes.
So that's true. If you force the dimension to be 1,
Right.
then it's what's called a deterministic strategy. And then convex combination of them is what's usually called the classical strategy. And you can take any rational strategy this way by just taking diagonal matrices with the exact proportion of where you want to. And you will see that if you do the Fourier transform, you'll exactly get, right? You have minus and minus ones on the diagonal, they will move to being zeros and ones. Instead of 1 and minus 1, they will become zeros and ones, and that's what the Fourier transform will do on them in the classical sense. So I hope that gave you something. Thanks, Irit, for relating it to classical strategy. But the important thing is that now we have a new decision problem, right? Given. So now you can define the following decision problem: quantum value 1/2 is given a game G. Decide whether supremum over all n-dimensional strategies. So for every n, go over all n-dimensional strategies. So you both take n to be as large as you want and all possible n-dimensional strategies. And you ask, what is the value? Where did I write the name? There, val GS. And the value of val GS. And S is an n-dimensional strategy for any. Okay, you take this supremum, you want to decide this is 1 or this thing is smaller or equal to 1/2. So that's your now new decision problem. And this is the complete problem for MIP star protocols. Okay, actually, that's the complete problem for synchronous MIP star protocols. So I forced something on the provers, but that's not how to show that synchronous MIP star is equal to MIP star. Yeah. It's That's less, because of some result of VDCAS. Maybe it,
No, I
maybe you
think
need MIP star is equal to
You
RE.
move from
Not
the
sure.
graph to its.
Anyway, that's synchronous
proper-
MIP star.
You move from the graph to a bipartite version of the graph. Non-synchronous strategies become synchronous.
Great, so this is the double cover of the graph, and you are right that.
Just ignore it, it's not.
No, that's a good observation. Then you can allow the two provers to use different strategies by just taking double cover. But you should ask yourself what happens to the value when you move to the double cover, the synchronous value. And that's not clear that it is, that it remains. Like maybe you go to the double cover, now they have better ways to win against you. So at least when you're focusing only on synchronous value, taking the double cover is not necessarily value preserving. Just a remark. Okay, anyway, so this is a decision problem. I have 10 minutes.
We want to reduce this to.
So I cannot reduce to this problem. That's our problem. If we could have reduced to this problem, we will just end up by saying now MIP star is equal to RE, solves everything.
We know a reduction from halting to this, given that it's.
That's MIP star is equal to RE. So MIP star is equal to
This
RE.
problem is MIP.
This is the complete problem for MIP star, for a certain subclass of MIP star called synchronous MIP star, but it's contained in MIP star, so it's enough. And this already contains the halting problem. So the way they proved MIP star is that all the games are what's called synchronous, and the optimal strategy against the synchronous game is a synchronous strategy. So essentially, this is the complete problem for the halting problem can be reduced to this. Yeah, that's the main result of MIP
The
star.
only thing you need to do is reduce this to subgroup test.
Yes, so that's the idea. Okay, so the idea is to find a version of qval 1/2 that reduces to softval theta. Yeah, that's the idea. So reduction from there to there. And we are not able to do the general case. We need to restrict the kind of non-local games you're allowed to use. That's the problem. And then we needed to reprove MIP star for this subclass. That's like why we have like a second paper that it will be on archive hopefully soon, but that reproves MIP star is equal to R. So what do we need? We need to change a bit the definition here. So let me do that. The way we change it is that we have two functions instead of one length function. Also, the length was important because of the unitaries, the way I choose representations. So, but now I have a readable length, LR, and a linear length, LL. Okay, so now instead of one function, one length for each vertex, I have two. So the answers produced by the provers have two parts, a readable part and the linear part. And the verifier, these functions cannot anymore be just any function that you want. I'll explain, I won't write rigorously, but I'll explain how does the D is allowed to work. So you have the readable part, maybe I'll dedicate more space for it. So in the answer of one player, I have its readable part, AR, and its linear part, AL. That's of length LR of X. That's of length LL of X. And B is also maybe other length. It doesn't have to be the same length. LR of Y. And here LL. Oops, that's not the correct L. L of Y. Great, so I have like 4-bit strings now. And the decision procedure must do the following. It first reads only AR and BR, so only the readable parts. Then it constructs a system of linear equations and checks whether the whole answers so the linear equations will be on the bits of the whole answer, and it will just check whether the system is satisfied or not. Now, again, those who know like non-local games, if you allow only readable parts, like if everything is readable, this is the same as a regular non-local game, because you read all the answer, you just decide whether to generate the system that always rejects or the system that always accepts, right? Like if everything is readable, that's like back to non-local games. If everything is unreadable, that's called the linear constraint system game. And actually it's known that if you could have done all of MIP star is equal to RE only for linear constraint system games, then there are non-sopic groups, for example. So it would be a huge deal to somehow push our whole proof such that there is only linear parts. Like that will already give you a non-sopic group. We don't know how to do it, and there are good reasons why we're not able to do this, but I can elaborate more. And this model somehow allows you to interpolate between like the most non-restrictive kind of games and the most, like the linear system games are very restrictive kinds of games. And now you should ask, okay, but now, like if I keep allowing you the same kinds of strategies, I didn't gain anything by this moving window between readability and unreadability. And the point is that for any readable variable, I'm going to force the provers to use just diagonal matrices. Okay, so think about it. There is here, so now it's the strategies are not from F2 to the LX to UN, they are from F2 to the LRX times F2 to the LX to UN, right? Now that's the kind of strategies. And I force the image of this thing, so all vectors that are supported on that side, to be sent only to diagonal matrices, only to ones minus ones on the diagonal. So the strategy should be, wait. The strategy should be classical on the readable bits. So now, if you try to push the readable bits to be everything, the possible strategies are just the classical strategies. So it reduces the value.
You said the input is a two-part thing.
Yeah,
So what do you mean an output for the first half?
I said vectors supported on the first half.
What does that mean? Zeros on the rest?
Yeah, zeros on the rest.
oh,
Okay.
I said vectors supported on the first part. Yeah.
I mean, it's a representation, so I guess you can like
Yes.
split it to like, write it as first half plus second half. So
Right.
like you are getting something for every.
Why first half plus second half?
It's a
The group F, like you can think of every element here as a linear combination of something that comes from here and something that comes from here, and then it's just the thing. Supported here is just the things that are. Anyway, there are many ways of seeing it, but just vectors that have maybe ones here, but all zeros here. That's what I mean. They must be diagonal. So what does it mean? It means that I'm forcing the provers. If you push the readable part more and more to the left, the provers have less and less strategies to use. Okay, like I'm restricting the provers in the kind of strategies they are allowed to put on the readable parts. And somehow this tension by restricting the verifier to have this format and restricting the provers to only have these kinds of strategies, now we can define tailored Q-val of 1/2. And this would be just, now we have a specific subclass of game, but a specific subclass of strategies. And I ask you to distinguish between value 1 and value 1/2. And this is the thing that we know to reduce to. So we have a map. I have 1 minute. We have a map that takes tailored game and translate it in a value-preserving way. And I'll explain what value-preserving in this context is, to a subgroup test. And that was the epiphany. Like once we had that, it was clear to us that although it is weird, it's a rich enough collection of games to redo everything in MIP star. It took us some time. The PCP wasn't off the shelf. Like we needed to invent the appropriate PCP that works. But other than that, like almost all of the work just was translatable to this more restrictive setup of non-local games. And once you can translate the tailored non-local games to a subgroup test such that it's value preserving, what do I mean value preserving in this setup? If it was 1, it's 1. If it was smaller than 1/2, it's not exactly smaller than 1/2, it's smaller than 1 minus some function computable that depends on the size of this non-local game. Okay, so exactly the kind of 2 to the minus size of the input kind of thing.
So this is the main step.
I see this as the main step.
Subgroups.
Yes, exactly. I think this is the main step, but now you need to reprove MIP. Just if MIP star was in this setup, it was great. We can just like cite them, but we actually reproved everything in this setup. That's like the second paper. So now there are two theorems. One, this is a value preserving map. And second, this is now tailored Q-val, whatever. Tailored Q-val 1/2 is like the Halting Problem has a reduction to this decision. Yes.
So how long should I think about the readable part? Like,
What do you mean? How long you
What's
want
the
to?
ratio?
like what's the ratio between is something known?
What do you mean something is known? Like in the end, we get for any Turing machine a game which is linear in the description, is a polynomial in the description of the Turing machine. So I don't know, like you can bound both the readable and the linear part by this bound.
I see.
Right?
No, I think he's asking you how close are you to.
For some
something
vertices, it's
that-
very important that for some vertices, everything is readable. And so for some vertices, everything is unreadable. That's actually very important.
Mhm.
Yeah, like, and that's because of the Pauli group. Like if you know from like, okay, so I can even write this group down. There are the X Pauli matrices. This is the X Pauli matrix and the Z Pauli matrix. You take tensor products of these of length k, you get what's called the Pauli group, like you take the product and so on. And these are already diagonal. So whenever there is an observable that comes from a Z measurement, that's okay, it can be readable. Whenever I have something that is mixed, that requires you both to measure somehow according to X and according to Z, as long as they commute, because only then it is possible, I force it to be unreadable. So if you know something about the MIP star proof, there is what's called question reduction there. It forces the prover to use representations of this group only for X's and only for Z products. Like for different vertices, one of them must be all the X tensor products, and one of them must be all the Z tensor products. Okay, and then okay, clearly this I can make readable because just the perfect strategies are already diagonal, and the other one they must be unreadable because these are non-diagonal matrices. So somehow just their proof method tells us which vertices, which part of the proof I can keep, I can make readable, and which part of the proof I cannot make readable. Somehow just follow their proof and you get it. Except for the PCP where it breaks down and then we needed to invent some stuff, but like that's essentially the only part you need to swap.
Let's thank Michael before we do more. No more questions.
I don't know if it's about post question, but I hear kind of two things. On the one hand, you're saying that at least you have some kind of program in order to prove the existence of a non-selfic group, right? That you could do this when everything was not readable, you would.
Yeah, that would be possible.
It would prove the existence of a non-selfic group in a non-constructive manner, right? It would just prove there's a separation between.
Yes, actually, no. It will give you a presentation of this group, just because the way MIP star is constructed, you will get these games actually give you relations, generators and relators.
Okay, so then.
You will get a group. That's amazing, I think. Like,
But in your setting of Aldous Lyons conjecture, can you provide me with an IRS, a specific IRS that is not in the.
We have the functional, and we can say something. That's a very good question. Like what's next kind of question. So we finally have objects that are non-sopic. Okay, so can we say something about them? The answer is yes. If you follow our proof, you learn something about these IRSs, but you don't know them completely. Like I don't have like a finite description that tells you like how this IRS is sampled. But just by it having value 1, ergodic value 1, I can already say something about it. I don't know if it's enough, for example, to tinker with Gottschalk conjecture, right? There is the Gottschalk conjecture version of IRSs. Okay, like this automata, if you remember, like the beginning of my talk yesterday, there's the Gottschalk conjecture for IRSs, and we finally have an object that you can tinker with and ask, okay, like we know that the Gottschalk conjecture is true for every sopic IRS, is it not true for this one? And you have enough information to maybe start playing with it, So I think there are follow-up questions. I don't see any follow-up way of tackling the non-sophie groups. That's just me. Like, I don't see how to translate it to a non-sophie group proof.
But what kind of
Because
information,
I don't see any way of pushing this. Like,
what kind of information do you have about this IRS?
for example, it contains larger and larger copies of Schreier graphs of the Pauli group. For example, so you know, in tilings, how they called those that you cannot translate?
Aperiodic.
Aperiodic, thank you. In aperiodic tiling, sometimes the way you see that aperiodicity is that every tile has a name. Like you can like say where is it put inside this, like, right, like infinite cascade of tile. And you have a similar thing here. You have a name for each vertex in your IRS. And the name comes from like the infinite amount of like the sequence of Pauli groups that are forced to have there. And my hope is that, okay, maybe we have a name for each vertex that you can read locally. If you are allowed to read enough radius inside your in your Schreier graph, you will learn more and more about your name. And so it's completely non-transitive. So there is a single like automorphism of this Schreier graph, like that swaps like a plus sign to a minus sign or something like that. But other than that, you can distinguish all vertices from each other. And so maybe this is enough structure, for example, to tinker with automatas, like now define an automaton on such a thing. Try to understand, maybe you can make it injective, maybe just by reading what is the size of balls. Like, I think there are interesting questions and they must go through the proof. Otherwise, like, you need some of the compression, self-reference, the techniques of MIP star to actually like learn something and maybe tinker with it. Yeah.
So what goes into the reduction from the modified Q-val to soft-val?
This reduction from here to here?
Yes.
Yeah, okay, so I already constructed things in a way that it's not hard to see. So essentially you can generate a generator for any bit of any possible answer at any possible vertex. Okay, that will be a formal generator. So I get a set S and I add one extra generator, and that's very common in quantum mechanics. You add like something that plays the role of minus the identity. So the generators are just all bits, possible bits of answers in all the vertices and a single extra generator. And then this generator, it needs to behave like minus identity. So it needs to be of order 2 to commute with everything, all the other generators. So these are two of the checks that we add to this subgroup test, right? I check words, whether they are closed or not. So I check commutators and square things. All the generators need to be squared, like they need to be of order 2. That's like the representation thing. And whenever things come from the same vertex, whenever two generators come from the same vertex, that's a representation of F2 to the LX. So I need them also to commute. I add all these conditions. Then readability. How do I read readability? In the Schreier graph, I want every readable object either to act like the identity or like J, like the minus identity. Okay, so I add this condition that the word either J times the generator or the generator itself must be in the subgroup. That's another collection of checks that we need to add. And then, because we have only linear checks, if you remember, like in linear constraint system games, there's also always a group theoretic way of seeing it. Like when you have a linear relation, replace the pluses by a product and replace the plus minus, no, that's what you need, all you need, right? Like you have generators, instead of taking their sum, take their product. That's all you do. And that's the words, okay? The system of linear equations will become a collection of words. And if it needs to be equal to 1, it needs to be a closed loop. If it needs to be if it needs to be equal to 0, it will be a closed loop. If it needs to be equal to 1, it will need to be equal to J. So I will take the product with J and I want to get back. So there is just a list of things that you can read out of these tailored games that generate a specific subgroup test. And it's quite intricate, showing that it's value preserving. You will see it requires some Fourier transform and understanding connected components in the graph only according to the X and Y generators, and there are some commutation things. So it requires some steps, but it's elementary. Like you can read it, you can understand it. It's not as if there is some deep mathematics behind it, but generally showing that this is value preserving. Yes.
So going back to, like, you define these two values, the ergodic value and the finite suffix value.
Yeah.
And I guess, like, if I wanted to prove this conjecture kind of more directly, you could say, I want to exhibit a single test such that the value for the ergodic one is 1 and the other one is like strictly less than 1.
Exactly.
That's not what you're doing, right?
That's exactly
And
what
you
we're
can't-
doing.
That's exactly what you're doing?
We can do it just because in MIP star they've done it. You take our algorithm that approximates, there is a way of translating our algorithm that approximates the ergodic value from above, translating it to a tailored non-local game, going through this mapping. And because it's a specific algorithm, we can bound all the parameters in it. We will get a specific theta, and we can say that this thing has value, ergodic value 1, just because of some abstract nonsense, and it has a sopic value strictly smaller than 1, just because you construct it such that it doesn't halt. So you do some game there such that it doesn't halt, and then it works
You
out.
just like kind of take the halting problem, like feed it back through the whole.
Yeah, with this algorithm, you somehow make this algorithm in such a way that you force it to not halt, and then it must map to something with sopic value strictly smaller than 1 minus theta, but its ergodic value must be 1 by some abstract nonsense.
Gotcha.
Yeah, so we actually have a specific subgroup test. And actually a student from, like a postdoc from Berkeley remarked that whenever you have a subgroup test, you can always replace all the challenges by a single challenge that just checks all of them. So even you don't need any distribution over challenges, you have a single challenge. As opposed to non-local games where asking all the questions simultaneously may hurt your perfect completeness, in a subgroup test, that's not true. Like if you check everything simultaneously, you don't lose perfect completeness. So actually you can have a single challenged game that separates the ergodic value from the sopic value. That's nice, I don't know, like it's like really a one check.
Well, it's just like treating a 3-set formula as one thing and not as many plots.
But in non-local games, you're not allowed to do it because the kind of strategies you have to have mutual measurability. Whenever you ask a specific question, you want things to commute. So they cannot, in a non-local game, you cannot ask all the questions simultaneously. But here somehow you can ask all the questions simultaneously, and still, if you won it before, you will still be able to win it. And it's, I don't know, I think it's nice. Hey, maybe it's not surprising when you think of it in a 3-set.
Okay, I guess we can continue for lunch, so thank you very much.